Okay. This is equal to omega naught t plus 1/2 alpha t square. Or you could also use this formula, whatever you want to use. Okay, so this tells you, so this is useful, for instance, in airplanes taking off and stuff like that. I mean, in the linear acceleration, this is how fast you're going. This was your initial angular speed. After this much rotation with this acceleration, that's how fast you're going. Okay, so this is angular speed as a function of position. So for instance, you saw this formula like this. So, planes have a takeoff speed. This tells you, given your acceleration, how long of a runway you need, and so on. Okay. So, but anyway, so you could use one of these two formulas. Okay, so. All right, I'll use this theta minus theta naught equal to omega square minus omega naught square divided by 2 alpha. So that was the angular displacement, 25 square minus 8.33 square divided by 2 alpha. And this will work out in revolutions. Okay. So after about 2,000 revolutions, it's going at that speed. Okay. By the way, so if you want, I can form study groups. If you talk to me, if you want to join a study group after class, I'm going to ask some people to lead study groups. Okay, and if you guys want to join a study group, just talk to me. All right. A flywheel slows from 600 to 400 revolutions per minute while rotating through 40 revolutions. What is the angular acceleration? See, in this problem, you'll use this formula. Okay, they give you the angle through which the speed change, and they're asking you for the acceleration. Okay. How much time elapses during the revolution? 40 revolutions. Okay. So in that one, you'll use this formula. Once you calculate alpha and you have omega and omega naught, you can calculate the time of flight. Okay. Again, for all these problems, all you need is these three formulas. Okay. And when are these formulas valid? When angular acceleration is constant. Okay. And the way you decide which formula you're going to use is, if you're trying to solve for one thing, you need to know everything else in that equation. Okay. And so that's how you decide. All right. So for instance, in part A, what is the angular? Okay, so it slows from an initial angular velocity of 600 revolutions per minute to 400 revolutions per minute and 40 revolutions. So you see they've given this, and that, and they're asking you to find that. Okay. So omega naught is 600 revolutions per minute equal to 10 revolutions per second. Omega is final is 400 revolutions per minute. And you divide this by 60. 4 divided by 6 is 6.7. Yeah, so okay. And 40 revolutions. So omega square equal to omega naught square plus 2 alpha theta minus theta naught. Okay, so omega is 6.7 square minus 10 square revolution square second square divided by 2 into 40 revolutions. So you see the revolutions will cancel, you'll get revolutions per second squared. Okay, so that's the magnitude of the acceleration. What is the negative sign telling you? It's slowing down, yeah. So you guys remember the right-hand rule? If the object is spinning this way, your thumb is pointing that way for the angular velocity, the acceleration is pointing in the opposite direction. Okay. How much time elapses? So if they're asking you for time, you got to use an equation that involves time. Here's an equation that involves time, and here's an equation that involves time. Okay, this one is a quadratic equation. Why do you want to fight with a tiger if you can, okay, if you have an easier thing to do, okay? So, and you see revolutions per second will cancel with that. You have a second there, and that second will come to the top. Okay, so in 4.8 seconds, it'll slow down to that speed. Okay, this problem says a rod of length 20 centimeters has 2 beads attached to its ends. The rod with beads starts rotating from rest. If the beads are to have a tangential speed of 20 meters per second in 7 seconds, what is the angular acceleration of the rod to achieve this? All right, so this is the rod, and there are these guys. There's the beads. Rod of length 20 centimeters has two beads attached to the end. And so R is equal to 10 centimeters. That's this length. Okay, the beads have a tangential speed of 20 meters per second in 7 seconds. 20 meters per second is it fast? Uh, yeah, it's 10 meters. So what you want to remember is 10 meters per second is roughly 25 miles an hour. Okay, 20 meters per second is twice the speed of Usain Bolt. Usain Bolt runs at 10 meters per second. Okay, so that's 50 miles an hour. Okay, in 7 seconds. Okay, for this guy, what you want to remember is the linear speeds. So the linear speed, this linear speed is related to the angular speed. The faster this is spinning, the faster this guy is going. Okay, and V is R omega. Okay, that's how the two are related. R is the distance from the axis of rotation. Okay, now in this formula, omega is in specific units. What are the units? Radians per second. Whenever you have linear quantities being related to angular quantities, that's always in radians per second. And this starts with this formula. You guys remember that? That's how the angle radians was defined. This S, R, and theta are related like that, okay? And here, theta is in radians. When you want to get this, you just take the time derivative of that. Time derivative of this is V. R is constant, and d theta by dt is that, okay? That's how you get that. And then if you want to get, if you take a second derivative, then you get tangential acceleration is equal to R alpha, okay? So you saw all of that. All right, so this guy has to be in radians per second, okay? So what we're going to do is, this guy is going at 20 meters per second. We'll find the angular velocity required for that, and then calculate the angular acceleration. So omega is and R is 0.1 meters, 10 centimeters is that, okay? So omega is, and again, you see the meters cancel, and omega is units of 1/2. The radians is a free label. Remember that, okay? Yep. All right, so now we want to calculate the angular acceleration, so we'll use this formula. Omega is omega naught plus alpha times t. Alpha is what we want to calculate, which is omega minus omega naught divided by t. Okay. Over what time did this happen? 7 seconds. Okay, so 200 minus, and what was your initial speed? 0. Okay, so this was radians per second divided by seconds. So all right, so essentially you had to know this formula to relate linear speeds to angular speeds, and then you calculated the angular acceleration. Yep.
So can we approach this problem a little differently
Mm-hmm.
by starting by just dividing by time? So that'll give you the acceleration is equal to R times alpha, and then divide by the 0.1 meter radius, and that should give you the same time. The same,
Say that again.
so if we start at V equals R omega, and you know that the delta V is 20 meters per second, you divide by time, that gives you an acceleration.
Oh, no, no,
Doesn't work.
no. Okay, let's see. So let's try it out. So you're calculating linear acceleration. Okay, so yeah, I guess it'll work out. But this is physically more intuitive. But what our friend is saying is calculate the linear acceleration. Okay, and you can do this because it's constant. And the acceleration is constant. So linear acceleration is, so that was meters per second over second. .86 meters per second square. And then tangential, so this tangential acceleration was r times alpha. Yep. Okay. This is physically more intuitive. Yep. All right. So the next problem says a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of static friction between the man's shoe and the merry-go-round is mu s is 0.5, how far from the axis of rotation can he stand without sliding? Okay. So again, so here's a guy standing there, and so when the merry-go-round is going around, so you're looking at the top view, it's spinning. When you go in a circle, are you accelerating at constant speed? You're going in a circle at constant speed?
Yes.
Why are you accelerating? Your direction is changing. And what is the direction of your acceleration? Toward the center of the circle. Okay, and so centripetal acceleration is v squared by r. And what does Mr. Newton tell you that if you're accelerating, what is it that gives the acceleration? There's a force needs to give you an acceleration. Okay? And then you just have to figure out where is the force coming from. Okay? Where is the force coming on this guy? He's standing on the merry-go-round. It's the static friction force. Why is it static? He's moving. I'm sorry?
Moving relative to the thing he's standing on.
No.
He's standing in one spot on the merry-go-round, and that spot is rotating.
Yeah. Also, he is not moving in this direction. Okay? And that's the direction in which you need the force. Okay, so for instance, if you were sliding in this direction and you had a force in this direction, okay? So here's a better example. If you're driving a car in a circle, you're moving relative to the ground, but you're not moving in that direction. Okay? But, I mean, what you said was right. In this, he's not moving relative to this thing, but what's relevant is he's not moving in that direction. So that's a static friction force. Okay. All right, so it's the static friction force. So now let's see. And now I'll draw a side view. So here's the guy. Here's the static friction force. And that should equal the centripetal force. What is the static friction force equal to? Mu times the normal force. The normal force is equal to his weight. Okay. So mu s times mg should equal mv squared by r. Look at that. Your weight your mass cancels. So as long as you're wearing those shoes, everybody can stand at that distance without slipping, okay? All right, well, let's now, to be able to do this, how is V related to omega? V is R omega, so R squared omega squared divided by R. So mu s is R omega squared. Yep.
By mentioning.
I'm sorry? Oh, yeah. R. All right, so here's the deal. Okay. Now, if R is 0, you don't need any stickiness. Everybody can stand there and you won't slip. Okay? So this could be an ice ring that's spinning and you could stand there and nobody would slip. For a given angular speed, and G is constant, these guys are constant. As R increases, the stickiness of your shoes has to increase. Okay? The further out you are, the harder it is to stand there. Okay? So this tells you what is the maximum value you can have. Okay? Did you guys understand that? Yep.
So the further out.
So in this equation, okay, so mu s is the stickiness of your shoes. Okay. So if this were infinite, okay, you could stand anywhere. You wouldn't slip. Okay. So this is assuming you're at the maximum distance when this is equal to that. Okay. So greater this number, further out you can stand. Okay. So this really is R max. Okay. And of course you can stand anywhere inside that thing. Okay. So how far from the axis can you stand with us? Okay. So R max is equal to mu s times G over omega squared. And mu s was 0.5, so okay, the radians is a free label. The second square will cancel, and you'll be left with meters. Yeah. So of course you can stand anywhere less than 0.78 meters away. Okay. And so let me ask you this. So you have a certain sticky shoes. What if we make the merry-go-round spin faster? What would you have to do? I'm sorry? Very good. Okay. So this equation says it. If you increase this guy, okay, this is constant, so you would have to decrease this guy. Okay. And if it's rotating infinitely fast, you'd have to stand at the center. And so this is also, okay, so here's something. If you want to clean your tires, if dirt is sticking on your tires, that's what you drive fast enough, your tires will get cleaned. Yeah. All right, so this problem says a system of point particles is shown in the following figure. Each particle has a mass of 0.3 kgs and they all lie in the same plane. So this is in a plane. What is the moment of inertia of the system about this axis? Okay, so, and the axis is perpendicular to this plane. If the system rotates at 5 revolutions per second, what is its rotational kinetic energy? Okay. The moment of inertia is given by this formula, MIRI square. It depends on the masses and how far the masses are from the axis of rotation. Okay. So, and the masses are all, so M R1 square plus M R2 square plus M R3 square. 0.3 kgs times 0.2 meters square plus 0.4 meters square okay, 63, it's 0.063 kg meter square. Those are the units. And then in part B, you want to find the kinetic energy of, so kinetic energy, the formula for kinetic energy is 1/2 I omega squared, okay? This is the parallel of 1/2 mv squared, okay? For rotational motion, m gets replaced by moment of inertia, which we just found. V gets replaced by angular speed, okay? And in this formula also, the angular speed has to be in radians per second, okay? So your angular speed is 5 revolutions per second. Each revolution is 2 pi radians, so that's 10 pi radians per second. Okay? So kinetic energy is 1/2 I is 63 into 10 to the minus 3 kg meter square times 10 pi radians per second squared. And so this is equal to energy is in joules, okay? 31.1 joules. Okay, a system consists of a disk of mass 2 kgs and radius 50 centimeters, upon which, so there's the disk, so that's a solid disk and it's uniform, and then upon which is mounted an annular cylinder of mass 1 kg and inner radius 20 centimeters, outer radius 30 centimeters. The system rotates about an axis through the center of the disk in the annular cylinder at 10 revolutions per second. What is the moment of inertia of the system? What is the rotational kinetic energy? Okay, the moment of inertia is the moment of inertia of the disk plus the moment of inertia of the ring. Okay. Plus ring. And you can look up the formula on that table. You have a moment of inertia for all standard objects. For a disk, it's 1/2 mr square. And for a ring, it's 1/2 r inner radius plus r outer radius square. Okay. So here's how you can remember it. If the inner radius goes to 0, what happens to the ring? It becomes a disk. If the inner radius goes to 0, the ring becomes a disk. If this goes to 0, that formula reduces to that formula. Did you guys understand that? Okay. All right, so let's calculate this. Mass of the disk is 2 kgs. Radius is 50 centimeters. 1 kg, 0.2 square plus 0.3 square. Okay. So that's the moment of inertia of this object. Then B omega is 10 revolutions per second, which is 20 pi radians per second. Okay. So kinetic energy is 1/2 I omega square. And this will work out in joules. Okay. Yep. You understanding? All right. Okay, in this problem, they ask you to calculate the torque about the z-axis. So here's the x-y axis, and the z-axis comes out of the plane. Here's how you determine a right-handed coordinate system. You use your right hand, and if you turn from the x-axis to the y-axis, your thumb points in the direction of the z-axis. Okay. Here's another way to remember it. If you turn a screw from the x to the y-axis, which way will the screw move? The screw will go inside like that. Okay. So that's the direction of the z-axis. That's a right-handed coordinate system. Okay, we'll use this in physics 2 as well. Here's a good way to remember it. Okay. In physics 2, there will be situations where you won't be able to turn your hands. So this right-hand screw rule is a good one to remember. Okay. So if you're turning the screw from the x to y-axis, which way will this screw move? Up. Okay. If you're unscrewing it, that's the z-axis. Yep. All right, so anyway, so all these forces out of the page at the origin given that F1, F2, F3, and F4, so here are these guys, okay. All these forces are in plane. Okay, so we're just calculating the magnitude of the torques, okay. So since in this diagram, they give you these angles and stuff like that. Torque is force times the moment arm. Okay. Here is the torque formula in R cross F. Here is the vector form of the equation. We're not going to use this because they've given angles and stuff like that. What is the moment arm? The moment arm is the perpendicular distance from the line of action. So if this is the force, this would be the moment arm. But what we're going to do is we're going to be smart about this. So here is the force, here is the point of action. We'll break this force into this component and this component. This component has zero torque because it's going right through the axis. Its moment arm is zero. So this component, the moment arm for this component is this distance. This force is perpendicular. The moment arm for this guy is that. What is the moment arm for this guy? Zero. He's going through the axis of rotation. So this is like trying to open a door by applying a force and pulling at the hinge. You're not going to open that door. Okay. And this guy will break it up into this component and that component. For that component, the moment arm is zero. For this component, the moment arm is 2 meters. And then here's another rule. If the torque, the convention is if a force is rotating the object counterclockwise, that torque is taken to be positive. If a force is rotating the object clockwise, that torque is taken to be negative. Okay? That's just a convention. You can go the other way. Okay? You can take clockwise torques as positive and counterclockwise torques as negative. But then you're not in step with the rest of the world. But you can. It's just a matter of convention. Okay. All right, so so the net torque is the sum of all the torques. They're all along the z-axis. Okay, so F1 times 3 meters, and so the moment arm is 3 meters. And what kind of torque is this? Is it positive or a negative torque? F1 is going to rotate whatever this object is clockwise, so that's a negative torque. Then F2 is going to rotate the object counterclockwise, and only this component has a torque, so it's F2 cosine 30 times 2 meters. Okay. F3 has zero torque. The moment arm is zero. And F4, it's a negative torque, F4 cosine 20 times 2 meters. So those are the torques. Okay. And so F1 is minus 3 times, F1 is 3 newtons, so 3 times 3 is 9, so that's minus 9. F2 is 2 cosine 30 times 2. Plus and F3 times 0 is 0, and then F4 is 1, F4 is 1.8, so 2 times 1.8 times cosine 20. And what are the units? I'm sorry? Newton meters. Okay, so here we go. Here's how we figure out Newton's meters. Okay. And what does the negative sign tell you? I'm sorry? Clockwise. The object will rotate clockwise. Okay. So the net torque is clockwise. All right, so in this problem, a seesaw has length 10 meters and uniform mass 10 kg. Okay, so when they say that, so what they're trying to tell you is where is the center of mass? Okay. I'm sorry?
Instead of 5 meters.
At 5 meters. So that it's at the geometric center. So if it was non-uniform mass, then you would have to calculate the center of mass using this this integral. Okay. Yeah. But for us, the center of mass is. So, for instance, if you become a civil engineer and then you will have beams that are sticking out, those will have non-uniform mass. Okay, and then you'll have to find the center of mass. But anyway, for us, it's at the geometric center. The resting angle is 30 degrees with respect to the ground. Okay. The pivot is located 6 meters at 6 meters. So this is 6 meters. Okay. So there is the center of mass. Okay. And this is 1 meter. There's 5 meters. What magnitude of force needs to be applied perpendicular to the seesaw at the raised end so as to allow the seesaw to barely to start rotating? Okay. So they're asking you what force do you need to apply here? So you're just rotating. Okay, so you're trying to rotate by this counterclockwise by applying this force. What is rotating it clockwise? The weight of the seesaw is rotating it clockwise. Okay, so there is the counterbalancing torque. Okay, now, so this angle is 30 degrees. Okay, so I'm going to draw blown up version of that. This is 1 meters, that is 30 degrees. So there is mg, and there is the moment arm. This moment arm is 1 cosine 30. That's the moment arm, okay? So, when it's barely rotating, barely starting to rotate, the net torque is 0. The net torque is 0. And the net torque is the counterclockwise torque, which is negative F times, what is the moment arm for this force? It's there, this is the axis of rotation, that's 4 meters. Very good. What did you get on the exam?
I got 80.
Why didn't you get a better score?
I didn't know we were allowed to have a formula sheet.
This was the second exam.
I didn't have it on the first one.
All right. All right. and then plus mg times 1 cosine theta, 30 equal to 0. Okay, so F is mg cosine 30 divided by 4. 10 kgs times 9.8 meters per second squared. Cosine 30. Okay. Oh, there was a meter there. Meters. Okay. All right, so the force you have to apply is 21.2 newtons. Okay, so this is 4 meters, and if you move this guy further to the right, if you made this 2 meters, would the force you had to apply increase or decrease? Increase. If you move this further to the right, this distance becomes smaller, this becomes smaller, the force you have to apply becomes greater. Okay. So you want to try and develop that habit. That's how you solve problems as engineers. You want to look at the equation and you change one variable and see what is the effect of that. Okay. And I mean, you would develop, I mean, you guys all knew the answer intuitively, okay? And you want to be able to see that in the equations, okay? Okay, so this problem says, suppose when Earth was created, it was not rotating. However, after application of a uniform torque, after 6 days, it was rotating at 1 revolution per day. What was the angular acceleration during 6 days? Okay. So omega is omega naught plus alpha t. Okay, this is 6 days, this is 0, this is 1 revolution per day. And you can calculate that angular acceleration, okay? Omega is 1 revolution per day. We'll keep it in revolutions. A day is 24 hours, and R is 3,600 seconds. Well, we'll just calculate in revolutions per day. Okay, maybe we won't even do this. Okay. So alpha is 1 minus 0 revolution per day. That's the angular speed. And t is 6 days. So this is equal to 1/6 revolution per day squared. Yeah, that's the angular acceleration. So what does this mean? Every day, the angular speed is increasing by 1/6 revolution per day. So 1/6 revolution per day. So when you start off, your angular velocity is 0. After 1 day, you're going at 1/6 revolution per day. After 2 days, you're going at 2/6 revolutions per day, and so on. Okay, so that's what that number means. What torque was applied? What was the angular acceleration? What torque was applied to Earth during this period? Okay, so torque is I times alpha, and You guys can look up, I believe, 2/5 mr squared. For a sphere of uniform density, the moment of inertia is 2/5 mr squared times alpha. Let me make sure. Moment of inertia of a uniform sphere. Yeah, 2/5 mr squared. Okay. So what is it? What was the angular acceleration? What torque was applied to the Earth during this period? Okay, so you have to look up the mass of the Earth. Mass of the Earth is 6 times 10 to the 24 kgs. Radius of the Earth is 6.4 times 10 to the 6 meters. And alpha is 1/6. Now you have to do that in radians per, okay, 2 pi radians, and 1 day square is, okay, I guess I should have, 1 day is 24 hours, 3,600 seconds square. Do you guys understand that I had to convert this to radians per second square? Revolution is 2 pi radians. 1 day is 24 times 3,600 seconds, and that has to be squared. Okay. So there's the torque you would have to apply. All right. Now, in this business, what you want, okay, at least I like this habit. What you want to do is you want to take care of powers of tens. Okay. This you can do in your head. If you try and put this in the calculator, it'll lead to trouble. Okay, so we'll make this 3.6. That's a 10 to the power 3. We'll make that 2.4. 10 to the power 4, and then this is squared. So 10 to the power 8 in the denominator. That'll kill that. And then 10 to the 22 is what you'll get. So 10 to the power of 22. What are the units for torque? Newton meters. Okay, so you have 2/5, 6, 6.4, into 1/6 into 2 pi into 2.4 into 3.6 squared. That was the rest of the stuff. Yep. So that is the torque you would need to apply to get the Earth spinning from 0 radians per second to 1 revolution per day, okay, in 6 days. By the way, when the Earth was first formed, it was spinning a lot faster. It was spinning in about 10 hours. Okay. So it's been slowing down. What's that? So the moon's gravity pulls and elongates the Earth. Okay? And now when the moon is over here, it has to go like that. So it was stretched in this direction, that had to stretch back, and then it had to, that's friction. That's slowing it down. Okay. As a consequence, so the total angular momentum has to be constant. Okay. So as a consequence, since this Earth is slowing down, the moon is going further away. What is the worst you can do? Lose the moon. And so the limit is 42 hours per day. 42 hours per day. That's the slowest Earth can get. But it's been slowing down. Okay.
That's over the course of like millions of years, right?
Yeah, billions of years. Yeah, the Earth is 4.55 billion years, so it happened over a couple of billion years. All right, so last problem. A clay cylinder of radius 20 centimeters on a potter's wheel spins at a constant rate of 10 revolutions per second. The potter applies a force of 10 newtons to the clay with his hand, where the coefficient of friction is 0.1 between his hand and the clay. Okay, so